Yeah. Now
Okay.
you're good to go.
Okay. Thanks, Mala, for that great introduction and for providing personal insight about my teaching. So thank you. Appreciate that. All right. So today I'm going to talk about the role of high throughput phenotyping in our program, which is a public breeding program. That's why I changed a little bit of my title, and I want to include, that I'm speaking from the perspective of a public breeding program. All right. So let me tell you a little bit about the program. So the program, we're working on pulse crop. It is a cool season crop that is adapted in cooler places and a little bit drier, such as North Dakota. And when I say pulses, I am working on, what I mean by that is field pea or dry pea, chickpea, and lentil. So these crops are not just a major crop in the US, but also it's a major commodity globally. Okay, and our lab mission is we want to develop and release new cultivars of pulses for North Dakota and nearby states. And the second one is we want to address major bottlenecks in pulse breeding and through cutting edge technology or new breeding methodology. And the third one is part of my teaching responsibility is we want to train the next generation of scientists for continued genetic improvement. As a breeder, I think I always want to know what the production look like on the crops I'm working with, because the idea there is because if there's no market, is there really a need to breed for that crops? Okay, if nobody is buying it, so or planting your cultivars, then there's no really sense to develop. All right, so as you can see here, I look on the USDA data, all the historical records all the way from 1928, as you can see here, until 2021. And you can see that all pulse crops, including dry pea, lentil, and chickpea, they have a very humble beginning. And then until 2016, there's a big shift, on the production. And when you sum them up together, the three crops has been planted in about close to 3 million acres. I feel like that's big. And that really, highlight the needs to develop new cultivars to meet these growing needs. And if you talk about the industry, how much is it in terms of valuation? I would say it is close to $1 billion industry. You look on the farm gate price level, and in the US, it is planted in about 3 million acres and then producing about 2.2 million pounds. And if you look on the market here, you can see that 60% is actually being exported, and then 40% is for domestic consumption. And these are the top exporting countries, okay, where US is delivering the product. And I think there's a great demand in pulses because of its nutritional value. And in the market, these are some of the products that you can find right now. So I really like chickpea hummus, for example, as you can see here. I really love it. And now it's becoming more and more functional because it has been integrated into product like pasta, ice cream, milk, wheat flour, and other snacks for breakfast, even soup. So you can see that here. And maybe some of you like the lentil soup. And perhaps if you get bored with your ice cream, you can try this chickpea ice cream. Uh, Let me know how that tastes. Okay, and most crops are front runners now in plant-based protein market, and there has been an increasing demand in the past 5 years. And one of the products that you can find in the market, including Costco, which is a wholesaler of products, is the Beyond Burger and Ripton here, which is a non-dairy milk. Mala, are you seeing my cursor here? My mouse? Okay, good, good. Just want to
Yes,
confirm that.
I'm seeing that. Yeah.
Okay, all right. And then the company who built this product is the Beyond Meat. And right now, if you look on this website, this product has a market cap value at $9 billion. And we are excited of this product because its major ingredient is beef protein. And each burger comes with 20 grams of protein, as you can see here. Okay. And similarly with Riptide, which is a non-dairy milk, was developed by Ripple Foods, and they were able to sell about 7 million gallons. I think that's a big market. And again, the major ingredient is beef protein. And in addition to that, pulse crops is becoming a popular choice in the pet food market in terms of being used as the input source. And one of the major reasons is it's cost effective. Okay, when I say cost effective, it's just a fancy term for cheap. Now, cheap source. We're competing with soybean. I think soybean is $14 per bushel at the farm gate price, I believe. And the peas, for example, the farm gate price is about $12. So it's $2 cheaper. And if you talk about a large number of bushels, so there's some cost that comes to that. All right, and North Dakota leads the nation in production of pulse crops. Just look here on the ranking. We are #1 in dry pea in the past 10 years. We are providing about 50% of the total US production. We're second for lentil production, North Dakota, and then third or fourth, depending you look at and the year you look at, for chickpea production. So you can see here, there are two major regions who the producer of pulse crops, the Northern Plains region of North Dakota and Montana, and the Palouse region of Idaho and Washington. And as you can see here, it started to go down all the way to South Dakota, Nebraska, Minnesota, Kansas, and even Iowa, you name it. So, all right. So now the question for this seminar is, why are we developing high-throughput phenotyping tools for applied breeding efforts? Maybe we're looking for a miracle, right? Maybe we're looking for a new variety, that could save the world. So, all right. So there are a couple of reasons I could think of. So one is every crop that you breed or any cultivar development process, it takes time, okay? In pulse crop, at least, it takes about 8 to 10 years to develop a new cultivar. And this is the elite breeding pipeline that we are implementing in the program. And this pipeline is similar to a funnel, as you can see here. And in that funnel, it comes with stepwise filtering all the way from hybridization, generation advancement, selection, progeny roll testing, preliminary testing, advanced testing, and all the way to release. Okay, and this funnel operates based on generations per year and the number of crosses you can make per year or number of line you can evaluate per year. And in addition to that, depending on the resources that you have, you need to take into account the number of locations and replications that you can evaluate your materials. And it always comes with a cost. And when it comes to trait selection, so here are the traits that we are working on, some of this. And at earlier generation, because of limited seeds, you cannot really replicate that much. Okay. And once you got enough seed, then you can perform replicated trial. And then for a more detailed evaluation of your breeding lines. When I was a graduate student, I don't know that this needs to be part of the breeding program. So every time you identify an advanced lines or promising lines, that could be potentially a cultivar, it needs to be increased. For example, for peas, we need to have about 2,500 bushels so that it can be released to farmers' field. That's a huge amount of seed. And again, I would like to emphasize here that it comes with a cost. And as you go down to this funnel, the cost is getting 5-fold or 10 times higher, I'd say. All right, so how about phenotyping bottleneck? Okay, when does a simple measurement of plant height becoming a problem? So when you go in the field, you have 1,000 plant. It's very easy to measure, plant height, right? You have a meter stick, put them, against the ground. That's it. Measure that. The problem is every season we have this number of lines. Okay, when you sum them together, there's about 8,200 plots. That's one crop. We have 3 crops. We have about 25,000 plots altogether. That's a major bottleneck, when it comes to evaluation. And another thing is, here it's just plant height, right? And at a given season, we are evaluating multiple traits at the same time, perhaps, at the same location. And so you could imagine, the amount of labor, the amount of logistics associated with it, right? I'm not going to talk about the breeding objectives that we got here because I just want to highlight the why we are developing tools. What are the bottlenecks associated with the typical conventional phenotyping process? All right. Again, one bottleneck is the huge number of plots. Second bottleneck is you are working on multiple traits, measuring it at a given season, at a given time. And how about this? There's just enormous logistical operations all the year round. So we are a small public breeding program, but we treat this as a small company. In every company, it comes with all year round activities, and you can see that here. So for example, we are now at November here. So we just sent out our seed actually to Winter Nursery in New Zealand. So after that, we're gonna start cleaning, processing a lot of seed for post-harvest quality, and then sending another seed set to Puerto Rico. And then, yeah, I'm not gonna talk about the details of this, but I would like to highlight that there's in running a breeding program, there's a lot of enormous logistical operations. Okay. And I feel like all graduate students who are listening right now could relate to this. It takes time to travel to and gather data in all testing locations, right? So this is the map of North Dakota, and we have about 8 testing locations. Again, we have 3 crops. So on the right side, you can see this Minnesota, and on the left side is Montana, and on the downside there it's South Dakota. If you want to go up, that's Canada. Okay, and the main campus is located here on the east side. And traveling from here to Williston, it takes 7 hours. So, and 7 hours without restroom. So if you take restroom or a break, that's gonna take about 8 or 9 hours. So your whole day is already gone. Okay, so when you get to the place, the plants are in different developmental stage. And so you need to get back so that you could capture the right developmental stage of the plants, right? So, and again, it's just, Williston is just one testing locations, and we have 8 of them. So, all right. And I think more importantly is this. This is the heart of I'd say, breeding program. It's the rate of genetic gain. Okay, for yield, I think plant breeders are doing a great job for increasing seed yield. Okay, but for qualities like seed protein concentration, the gain that we got so far is almost 0. Okay, I feel like that is a clear breeding objective, given the fact that there is an increasing demand for high protein peas or high protein chickpea or lentil. Okay. All right. So I told you earlier that a breeding program is like a funnel, and it works so that the width of the panel is proportional to the amount of diversity you can evaluate, and the length of the panel is proportional to the time it takes to release a cultivar. Okay, and we want to develop and transform this funnel into something like this. It has a wider mouth, okay, and shorter length, so that we could release new cultivars as quickly as possible. Okay, and how are we going to do that? I feel like there's a lot of new tools right now. There's a lot of new hype for new tools. But I feel like my quick message here is using the right method or breeding tool to whatever task you're working on may be the key for increasing rates of genetic gain, at least in pulses. Okay. And as you can see here, we are evaluating multiple technologies. And we have high throughput phenotyping, targeted gene editing, genomic selection, and speed breeding. Okay. But for today, I'm going to talk about this high throughput phenotyping. All right. So I was asked by Mala to define what high throughput phenotyping means. I feel like I'm going to answer that from the breeding perspective. I feel like for me, high throughput phenotyping is when you develop cost-effective, easier, and more objective method for collecting accurate, easily interpretable data, and at the same time, it should be biologically meaningful. Those are the characteristics that as a breeder, I'm really interested in. And right now, these are the technologies that we are exploring in the program. We have a drone with multispectral cameras. Mostly the target traits here are the above canopy traits. And we have a photo booth we just developed by one of my grad students for assessing seed quality traits, which is really cool. And the other one, the problem with a drone is it doesn't capture the phenotype under the canopy. And I feel like the rover like this would be very useful for that purpose. Okay. All right. So we are working on multiple traits, but for this presentation, I'm just going to focus on two: maturity date and post-crop diseases with visible foliar symptoms. Okay, these are some of the, I would say, low-hanging fruits because the symptoms are highly visible from the top, and it can be easily captured by drone imaging. All right, so let's talk about the Phanomasis root rot. This is really a devastating disease in dry pea that can cause up to 100% failure in crop production. And as you can see here, that once the plant is infected by root rot, the symptoms are showing, the chlorosis and necrosis are showing from the top. And I feel like this could be one of the traits that we could target, by a drone. This is, by the way, is under field condition. And the problem of evaluating, breeding lines for disease is you cannot control the environmental condition for conducive development of disease. So if there's no disease, so there's no way you can evaluate for resistance for any disease you are interested on, right? And so what we did here is, instead of doing it in the field, we brought it to the greenhouse. And I have fantastic collaboration at NDSU. We have Dr. Julie Pasci, who are our plant pathologist, and Dr. Paulo Flores, who is faculty in agricultural and biosystematics engineering. Okay, so one of the criteria that we are looking at for a platform is it should be cost effective. It should be cheap. So we bought a typical, RGB camera, put it on the ceiling of the greenhouse, and it moves along the rail, left and right. Okay, and the movement that it has allows to capture the full greenhouse, and it can capture the images like this. All right, so the single row here is a single line. We have, for each line we have about 7 plants. Okay, and then we replicated this because we have a lot of lines, like about 1,000. We replicated it by time. Okay, and then you can process the images. You can break it by plot, and then create an orthomosaic images, and then create some indices you can find here, and then need to isolate the noise and only focus on the plants. And then at the end of the day, what you would have is something like this, the numerical values that can be used for any downstream analysis. Okay, and to compare that with conventional scoring of propionamyces root rot, it is a very tedious process. So after inoculation, you need to destructively sampling the plants. Okay, need to harvest that, and then you need to clean the roots, and then the visual scoring of the symptoms are being done. So we are using the scale of 0 to 5, and just to give you an idea, these are the scores. The 0 is the healthy one, the 5 is the worst one. So in between are those that showing a little bit of symptoms. Okay, just to clarify here, so we are using aerial symptoms on the leaves based on the images, and then trying to correlate that with visual scores on the roots. Okay, and the reason we're doing that is because we don't want this scoring to be destructive. And the only way to do that is we can capture, the symptoms. One of the ways to do that is if we can capture the symptoms from the top without necessarily, taking out the ground roots. Okay. All right. So first of all, here are some of the results. And the first question we got is, are the distribution biologically meaningful and maybe comparable with visual scores? I think the short answer is yes. There's some good correspondence between the HTP indices and then the visual indices, including the disease severity index and the rated visual scores. Okay, seems to me there are all following normal distribution, which is a typical characteristic of a complex trait. And are the HTP indices biologically meaningful? So Dr. Barry is the one working on this. And what we do here is we estimated the heritable variation for each trait and for each indices and for each index. And as you can see here is the y-axis is the heritable variation, and then the x-axis is the number of replication. Okay, we want to know how many reps do we need for the optimal heritable estimation. Okay, if you look on the overall trend, you can see that the yellow, which are the HTP indices, has always higher heritability versus the visual score. But take note that not all HTP indices is actually helpful. Some of these are not helpful, like this one here, the EX excess red here. It's not useful because the heritable variation is really low. And then the number of replication here, so you can see that whenever number of replication you look at, the EXG and EXGR indices have always higher heritability. And when you talk about, resource allocation, effective allocation of resource in the program, how many replications do you need? It seems to me that you need more, I would say twofold, for visual scoring just to match the heritable variation captured by HTP indices. That's the message I'd like to convey here. And another question we had is, if heritable variation can be increased, can that be translated into increased power of genetic mapping? Okay, and these are the visual scores from the Manhattan plot. We do GWAS. I think this is just a typical QK model, I believe. We run multiple models, but for this one, I think this is just a QK model. And you can see that if you look on the signals or the SNPs identified, HTP indices, GWAS for HTP indices identified more associated signals over the visual scores. I think that's a good result. And we are interested to know whether those signals could correspond to meaningful genes. And the quick answer is yes. Those genes that we put here are related to disease, I would say, development. So, which is a good sign. All right. All right, that's my first story. And the second story is the using of low-cost UAS-based RGB camera to estimate maturity date in Gold P. Again, the major bottleneck here is we have about 26,000 plots. We're evaluating 25,000 plots we're evaluating yearly. So this is just some of the capture that Harry got. Harry is a graduate student in our lab. And just to give you an idea that, see here at maturity, you can essentially identify which one is early, which one is late, just based on the color of the images. All right, and this based on 700 plots. And I think this is the diversity panel. We want to use the diversity panel because the amount of variation per maturity is substantial. All right, so just to give you a simplified workflow for processing these high throughput images. So you have a field, you know, you have plants or whatever crop you work with, you plant them in either field or greenhouse or maybe growth chamber, if that allows you. And then whatever platform you're using for collecting data, whether you have a drone or robot, you need to collect that, and then you need to process and stitch the images, for example, come up with the orthomosaic images. And then your goal is to transform that into numerical phenotypes so that it can be easily grasped. On one side, in parallel, I would say, you are also gathering ground truth phenotype data, and then after you run the experiment, you do some data quality control and whatever statistical analysis to get the adjusted data like blues or black. And then both numerical phenotypes from HTTP platforms and analyze phenotypic data, you can do a quick correlation and see what the correlation looks like. And you can do all sort of downstream analysis, for example, genetic mapping, okay? And this preliminary results, and so far this is the pipeline that Harry built into this platform. And it's pretty much, you know, the same workflow that I mentioned, except that it's more detailed. For example, for image collection, you can see the B here. We need the ground control points installation because that is a reference later for tracking the images. And then this is when he getting ready for the flight. And these are the raw images. And then after that, you're gonna process that, get the mosaic image using Pix4D, and then calculate the vegetation index using NDI, and then plot layering and masking, and then extracted the numerical value, and then downstream analysis using whatever software you want to use. Okay, and there's another way. I got this from Dr. Paulo Flores. There's another way of showing how the process works, but I'm not gonna talk about details of this because it's pretty much what I mentioned on this slide. All right, so at the end of the day, what you would get is something like this, a table like this, and this is your plot ID and all the indices that you got from your HTTP data. And in this case, there are about 38 vegetation indices, and that numbers varies according to the sensor that you use to collect the data. You have RGB, hyperspectral, thermal sensor, you name it. All right, so we are interested to know whether we can use any of those indices, the aerial index, to predict maturity date. And as you can see here, the correlation is pretty good. These across maturity groups are getting about 0.87 R squared. So if you take the square root of this, I think it's going to be about 0.9, I'm guessing. So the correlation is good. And we are interested now whether how good it is to predict within maturity groups. So we have 3 classification. We have early, mid, and late. The mid is the red ones. And you can see that the early ones could predict really well, that the HTTP, the drone imaging, could predict the early ones pretty well, similarly with the mid ones. But as the accessions, as the maturity tends longer, the R-squared value tends to get lower. I think the reason for that, it's because the index relies on the greenness, the decay of the greenness of the leaves. And so the late ones always has a lot of green leaves throughout the season. Yeah, that's, I think, one of the major reasons on this. And of course, you can take into account the heterogeneity in the plot. Maybe there's some segregation there. There's some weeds. Those are another compounding factors that you need to take into account. All right. Okay, that's my second story, the maturity date there. And the third one is, so Mario Morales, a PhD student in our lab, is developing a great tool for assessing seed quality. He developed a photo booth with high definition cameras. And so what it does is you put the seed in a Petri dish, and then you put it inside, and then, yeah, and then it captures a lot of variable associated with the seed. And I feel like it's really cool. I think that it has a lot of application. And another thing I like about this platform, it is very cheap and easy to set up. I feel like any public breeding programs can utilize this. All right, what is the rationale and why we're doing this? So in pulses, the seed quality, like seed size, for example, determine the market classes. Okay, so in simple word, market classes are just simply, the different, the product, that you're aiming to develop for, kind of product or cultivar. And in lentil, for example, we have three. We have large lentil, we have medium lentil, and we have small lentil. And so what we do here is for each cultivar, so each line here is a cultivar, okay? So what we do here is get 200 seed, so measure the percentage of seed that would pass through the sieve, and then create a density curve like this. And one quick message here is seed size is following normal distribution. And this is expected because it is a complex trait, right? How about those lines that follows a bimodal distribution? So like this, for example, here. Okay, could be two reasons why it has a pattern like that. One, there might be segregation. So your seed is not uniform yet. Or two, your sample size is not good enough. So you need more seed so that you could really observe, the pattern of seed size. Okay, and when farmers buy seed from licensing company or whoever is selling the seed, they should not be expecting uniform seed size of seed. And for the reason of, because of this, seed size is a complex trait, and you should expect to have some distribution like this. Okay. And I feel like the platform that we are developing here, if we can automatically get the seed size of this, if one of this, and then create an image like this, then from there we could identify right away which one has a mixture like this, and which one has has higher amount of large seed, has lower amount of small seed, and so on. Those are the applications. Mala, how much time do I still have? So good. Okay.
Yeah.
All right. So now I mentioned about that the drone can capture the above canopy, but it doesn't really capture the under canopy traits. Okay. This is an area of research that's still in progress. And this is actually in soybean. Okay. And we bought this robot, and it's designed for capturing any traits that can be captured under the canopy. Okay, and in pulses, what we're targeting for is to count the number of pods in pulses. And pulses in terms of architecture, in terms of pod, I think it's pretty much, I'd say similar. It has some similarity in soybean. So I think if it's working pretty well in soybean, it should work as well in pulses. So just to give you an example here. So it has a LiDAR. So it's allowed to get some information, an extra layer of information. And so from here you can see the size of the pod, right? And the size of the seed in the pod, which is, I think, very fantastic. And then I think if you can cut the number of seeds per pod, I think that's really great. And it could be translated to higher yield later on. So, okay. And you can also do some 3D approximation using that robot. So, which if you're interested to know the amount of biomass that each plant has, then I think you can use that robot to model, the biomass or any plant structure within peeled plots. Okay. All right. And then I think these are the last of some of my two last slide, I believe. I feel like, from my perspective at least, high throughput phenotyping would be important later to better characterize G by E. Okay. So in a program, you have tested environments and you have untested environments, and you also have tested genotypes and untested genotypes, right? We're trying to predict untested genotype most of the time. And if you want to be challenged, you want to take into account the untested environment at the same time, right? I feel like we're always predicting untested environments because every year we don't know what's going on, what's going to happen. Even though you plant in the same location over and over again, because of different environmental profiles, it's going to be a different environmental condition. Okay. And here, because you test your genotype, you can estimate your G by E. And I feel like any information you can get here with high throughput phenotyping can help with to better characterize G by E. Right. Here, you cannot estimate G by E, but what you can do alternatively is you can characterize the environments, okay, where your plots are. You can get your temperature, relative humidity, etc., and so on. All environmental parameters you can think of, whether it's going to be on daily, weekly, monthly, or in a seasonal basis. All right, and in North Dakota, I think Mala could totally relate to this. North Dakota, the climate is continental and it's characterized by large variation in temperature, precipitation, and airflow. So this is just based on the amount of precipitation I think we got in the past 20 years. And you can see that the east side it's receiving more moisture. The west side is a little bit dry. And in the middle, of course, the gradient it's different. So the gradient in terms of increasing rainfall is from west to east, the amount of rainfall is increasing. So I feel like this is a totally different environment, another different environment, and this could be another different environment. So maybe 3 mega environments, if you will. All right, so now the challenge is, I'm not gonna bore you with this image here, okay? The challenge is how can we redesign, our program with these new tools, okay? All right, my focus is on just high throughput phenotyping here, which I use drone to represent high throughput phenotyping activity. Okay, so this is your typical variety development pipeline. Start from the cross, generate F1, then the inbreeding phase, and then your F5, and then your start up your yield trial until you release your line, right? And so I feel like in the program, so your program is like a machine. Okay, if you want to integrate something, you make sure that the machine will run effectively or better. Otherwise, if you're integrating something that would slow down the machine, then it doesn't make sense. Okay, so right now, the way we integrate this is the high throughput phenotyping. We're integrating that, we're utilizing that from the preliminary yield trial up to the regional trial, and even up to the release. because when you release a line, you need to track the uniformity. You need to make sure that there's no possible segregant or any contamination on your seed or plants. Okay, and again, I mentioned this, that we are utilizing this for tracking phenology, disease resistance, and better characterization of G by E. And I feel like phenotypic selection, whether it's through the use of HTP or manual measurement, I feel like it's becoming more important here at the later stage of the program, because you want to see your plants in the field. I don't want to release any cultivar that has not been tested in the field. Okay, and again, this is pretty much to be continued. I'm a new faculty. I've been here for about, I'd say, getting 4 years, and it's been so good. And the take-home messages here is breeding requires adapting false crops with ever-changing environments and ever-evolving pathogens. And how do we adapt? I think we develop new breeding strategy and methodology. Collaboration is always beneficial for farmers and the community. And then we are carefully rethinking and redesigning every aspect of the breeding program in context of cost-effective resource allocation. And I think this is one of my, I think this is the last slide. I'd like to end with this, okay? Every technology that comes, to the community, it comes with a hype, okay? Or excitement, if you will. And then if you haven't read this paper, I would encourage you to read this Dr. Rex Bernardo's paper. It's really awesome perspective, insights. And every technology, it comes with 3 phases: the excitement phase, the realization, and the reality, okay? And then if you were one of my students, my question to you is, high-throughput phenotyping is a new technology, right? So if you are going to predict what would be the fate of this high-throughput phenotyping technology, do you think it would follow the same trend, like for association mapping, linkage mapping, or QTL, or genome-wide selection? Or do you think it would go the trajectory or going up? I will leave that to you as a question or something to think about, okay, when you leave out of this presentation. All right, and I have an amazing team at NDSU. I could not be, happier. And for my high-throughput phenotyping talk, I'd love to highlight the persons here: Abdullah Berry, Jungwa Kim, Sekiro Atenda, Mario Morales, and Harry Nebraska, all fantastic members of our lab. And at NDSU, we have a lot of fantastic collaborations, a lot of great science we do, fantastic. And we are supported by Northern Pulse Cover Association, we have a lot of USDA grants, USDA Crop Germplasm Committee. Then we got funding from Foundation for Food and Agricultural Research and NSF. So with that, I would love to end my presentation. Thank you.
Jean, would you like to go ahead with the moderating the Q&A?
Yes. So first of all, thank you, Dr. Bandilio, for that very wonderful and very informative talk. So prior to this lecture, we asked our registrants to give us what questions do they have. So we selected a few because, of course, we cannot run through all of their burning questions. Right. So first, you have mentioned a lot of advantages of high-throughput phenotyping. So are there any potential disadvantage of using high-throughput phenotyping when it comes to phenotypic data collection?
Yep, absolutely. Are you familiar with 5Bs? So it's a concept being used in engineering. So when it comes to data gathering, there's a concept called 5 Vs. The Vs stand for volume, veracity. I'm trying to recall what those are. You can just search on the internet, okay, later. And I feel like when you take into account those 5 Bs, high-throughput phenotyping will always win over the traditional or conventional scoring, okay? Volume, for example, you would get a lot of data. So you can get data at multiple time points, okay? You could get data at in 1,000 plots very quickly, maybe in 20 minutes. You can do that, which is not possible with conventional, data gathering, unless you have a lot of people to work with you, which is in the case of public bidding program, that is not entirely possible. Okay, and then I think the application of this, it all comes down to the cost. Okay, with the amount of data you generate, is it really translatable to being cost effective running a program, or can you speed up the program? I feel like the answer is yes.
All right, thank you, Dr. Bandilo. So we also have, in connection to that, what could be the major challenges in implementing high-throughput phenotyping technologies, primarily UAV-based, which I think you've shown, for plant breeding programs in developing countries?
Oh, developing countries. Well, how about we start with developed countries? Okay, and then we go to developing countries. Okay.
Yes.
So here, for example, so my answer would be an insight from my program, from our program here at NDSU. Okay, when you use a drone, you need a license. That's one thing. So make sure that before you apply a drone, you fully understand what you are doing, and it should be something that you just do instantly. Okay, because you want to do it. No, it's not a straightforward process. There's a license. Okay, second, so once you get the license, now you can fly. What are the expertise you need? Okay, is there a person you can rely to, so that if you have a new grad student or postdoc, something you can train with? Okay, so right now we are collaborating with Dr. Paulo Flores, who is from the Department of Engineering. And I think once the skill set get transferred to our program, then it's like we are going to transfer that to every member in the lab. Okay, and those are the second thing. So if there's no expert you can rely with in your department or in the university, then this may not work unless you can talk with private company. Okay, the difficulty working with private company is sometimes they're working on multiple, target customers. It's not fast sometimes, and data sharing process can be an issue. Okay, all right. So the third thing is the data analytics. Again, so when you buy a drone or any HTTP product, so make sure sometimes you can pay more, and it comes with data analytic support, which is really cool, because at the end of the day, what you want is just the numerical phenotypes that you can use. Or other option is you can actually learn the process. If you're a graduate student or who wants to learn that, then you can actually learn that. There's a lot of public resource that you can outsource. Okay, so now extending that, those are the three things I could think of. And then I think last but not the least, I would say is the price of actually integrating this. Okay, this is your program. Let's say the drone that we bought cost me $20,000 with all the sensors that you need, $20,000. If you don't have that resource, then it may not be possible. So extending that to the developing countries, I feel like if developed countries has that issues, I think we can count more issues with developing countries, right? I'm not trying to underestimate or anything, but I feel like those same issues will hold true in either you are in developed or developing countries, unless you're working in private company where you have a lot of resources. Okay.
Thank you. Again, in relation to that last question, so if somebody would want to try high-throughput phenotyping and include that in their breeding program, so what tools are there to rapidly introduce and apply high-throughput phenotyping into their breeding program? So probably they're asking what HTP tool they could start with.
Right. Yeah. I think, as a plant breeder, I'm always looking for a low-hanging fruit where I feel like the technology that I have will be more effective. So right now in the program, at least, we're using this for maturity and diseases with highly visible symptoms from the top, like what I showed here. Okay, I think the under canopy rower it's still in the earlier stage, and it will take more time. And I feel like the drone will be really, really useful. And I think the setup in the greenhouse will also be very useful for the reason that you can control the condition in the greenhouse.
All right, thank you, Dr. Bandilio. I think we have a lot of good questions from our participants right now, so I'm turning it over to Andy.
Yep, I got a couple for you. In relation to your broader pipeline in your last few slides, if your interest involves to improve field testing and selection accuracy, what is the aim of doing genomic selection prior to making selections using extensive field testing? Does that make sense?
That's awesome.
Yeah.
That's a great question. Okay. The way I look at it is when you do genomic selection, it's based on the SNP data or whatever data you could tie up with that. It's before, so you make prediction before you put the plants in the field, right?
Yep.
So now you put the plants in the field. That is, I think, high throughput phenotyping would come into play. Okay. And as you get more and more data in your program, you have high throughput phenotyping data, you have SNP data. You could, combine that together, those information, and come up with a more powerful prediction framework. Those are my 2 cents.
Makes sense. There was another question.
And also, can I add one more thing?
Go for it.
I think at the earlier generations of the program, we're talking about 10,000 to 20,000 appliance, and we are a small public breeding program, right? And even if you use high throughput phenotyping as a drone for those, limited replicated data, if you're assessing yield, can you actually use that for yield assessment? Chances no, but I think that is where genomic prediction can be more useful.
Yeah, I'd agree with that. Makes sense. There was a question regarding machine learning and what models you were using in pod count.
Pod counting?
Yeah.
Okay, we're still working with a developer, Patera Cynthia, and we're developing our own framework. We're trying CNN, the convolutional neural network. I think random forest can also work just fine, but we are trying to compare multiple algorithms. We are still on developing phase, exploring phase. So right now I don't have any data to support that claim. So
great. And then I've got one more that hasn't been answered yet in the chat. And then it was on your winter nursery and why you're choosing to go to New Zealand for your location. Is it because of specific weather patterns there? Or are they one of the top pulse producers in the world? Or is it just because you have collaborators there?
Right. So before we finally arrived to that location, we've tested to multiple locations. Okay. We sent seed to Hawaii, to Arizona, and then Puerto Rico, what else? Argentina. Well, the amount of produced seed, it's not really a lot. That's one thing. So the adaptation is one thing. It's not really fully adapted. Again, Paul says peas and lentil, they are cool season crops. Okay, it needs cooler, drier environment. So if the environment is not like that, it's not really going to do well. So adaptation it's one thing. Not because New Zealand is great.
Yeah.
Maybe we have time for one more question.
Jonathan, I think everything else has been pretty well answered.
Yeah. So I think this is one thing that I'm also interested. So how much does selection accuracy increases when using high-throughput phenotyping and genomic information?
Okay, that's a good question. That's what we're trying to explore. At what level of accuracy, the high throughput phenotyping would be effective? At least for maturity, I think I would say 80%. Okay, so now let's say your accuracy is 50%. Okay, and if you want to use the data, okay, you can just develop some level of framework. Are you seeing my hand?
Yeah.
Okay, so you can create a fancy, diagram or whatever. You have x-axis for the observed, or maybe indices, y-axis is the observed, and then you have multiple points there. And then you could come up, let's say, I want to use 30% of my lines. I want to select 30% out of 1,000 lines. I want to select 30% based on maturity. Okay, so from there you could assess how many of these are actually, perfectly hitting the right maturity dates. Okay, so I think if we go down to 50%, I feel like we're getting to add some noise based on maturity alone. And right now, I think we're looking at 80%. And that's what we're getting, particularly for early and medium maturity groups. For late ones, when you the indices is relying on the decay of greenness. Okay, and the problem with that is with late maturity group, it is always green. The plants are always green until the end of the season, and we use some chemistry to burn them down so that we can harvest. Okay, so if plants still look green, then chance is the accuracy would go down, your selection would not be meaningful. And you're not going to select any, at least in North Dakota environment, you're not going to select any late maturing varieties anyway. So
I think we are up with the time. With this, I would like to conclude today's session. Thank you, Dr. Bandilio, for such a great and informative talk. Now I think we have more insight, like why, when, and how we can use high throughput phenotyping for phenology, disease resistance, and better G by E characterization. So thank you very much. So before we end, I would like to share this slide. So you can connect with us on social media and stay tuned with our upcoming events. And some people had question about the membership. If you see a link in chat, Andy has shared a link where you can go and become a member. And it is very less for student. It is only $45 to become a student member. So I highly encourage graduate students to become NABP members. So thank you. Thank you everyone for joining us today. Yeah.
all right. Well, thanks again for the invitation.
Thank you.
Right?
Great talk.
Yeah.
Yep.
Yeah.
Okay.
We'll see you guys.
You can stop recording, Andy.
Yeah.